This is a simulation of a single-stage distillation column that separates a binary mixture of aniline and butanol, which you can see labeled here at the column inlet. This is a two-part lab where in part 1 you will create 3 process models, one for each of the 3 process controllers, those being a temperature controller, a pressure controller, and a liquid level controller. In order to model these processes, you will gather data from step change inputs to the manipulated variables. For the temperature controller, the manipulated variable is heat duty. For the pressure controller, the manipulated variable is distillate valve lift, or how open the valve is. And for the level controller, the manipulated variable is volumetric flow rate of the bottoms stream. After gathering your data, you will determine the process model for each controller and then use least squares regression to find the process gain and process time constant. Depending on which process model you use for each controller, there may be more than one gain term or time constant term, as you can see by the inverse process model, which has 2 terms for the gain and time constant. Some models may include other parameters, such as time delay, but since this simulation has 0 dead time, such terms would be unnecessary to describe the processes. In the second part of the lab, you will use a discrete time method to implement process control of the 3 process variables, which are column temperature, column pressure, and liquid level. Your first goal for the second part of the lab will be to determine the appropriate gain and time constant for each controller and to input the appropriate control law using pseudocode. Your second goal will be to test your controller tuning parameters by introducing deviations to the inlet conditions or by adjusting controller set points. Your findings will be submitted to your instructor in a lab report. Going back to the first part of the lab, you can see that there are 3 graphs at the bottom of the page, one for each of the 3 process controllers. Each graph displays the manipulated variable in blue and the process variable in green. The manipulated variable is drawn with respect to the right side y-axis, and the process variable is drawn with respect to the left side y-axis. For example, in the pressure graph, the green pressure line corresponds to this axis on the left, and the blue valve lift line corresponds to this axis on the right. The x-axis displays time, with the value of 0 referring to the present time, and negative values referring to historical values. The controller parameters and inlet conditions may all be adjusted by entering a value into the respective input box and then pressing the Enter key, or alternatively by pressing the Update button. Let's introduce a step change input to the distillate valve lift and see what happens. As you can see on the graphs at the bottom, increasing the valve lift causes a decrease in pressure because vapor is able to leave the column more rapidly. You can speed up the simulation using the slider at the top, with the default value of 1 corresponding to real-time simulation, and the maximum value of 20 corresponding to 20 seconds being simulated per second. This slider has no effect on the data or process, it just acts as a fast forward to use as needed. You may also set it to 0 to pause the simulation. The data from your trials can be downloaded as a spreadsheet by clicking Snapshot CSV, and your data will look something like this. It'll have a maximum of 1,000 rows, so keep in mind that the snapshot will only include the most recent 1,000 seconds of data. More detailed information for each part of the experiment is provided by clicking the Directions button here, underneath the Snapshot CSV button. Finally, if the font size is too small or large, you can adjust it by zooming in or out in your web browser. On Windows, the shortcuts for zooming in and out are Control minus and Control equals, and on Mac, the shortcuts are Command minus and Command equals to zoom in or out.